Okay, so let's do a very beautiful thing about the relationship between the dot product and the projection of a vector on another vector. So the dot product is one of the key elements that we can use to see the projection of a vector on another one. But there is a problem. And this is a very beautiful one because we are going to connect the dot product to the projection formula. You can see here the projection, here is the dot product. So as you know, the dot product is a very beautiful one. It's an inner product between two vectors. The dot product is just every element multiplied by the element of the other vector and sum that all up. Now, what it gives you geometrically is the norm of A times the norm of B times cosinus theta. So just for you to see this beautiful way to see the projection, think about two-dimensional Cartesian space or two-dimensional space where here is A. You can see my writing is very, very beautiful. And this is B, okay? Now, theta is between those two vectors. Here it is. And when you take the cosinus of theta, what you get, if you think about it, is cosinus theta is this. Here it is A, here it is B. So cosinus theta is this. A cosinus theta, let's call it like this. Okay, this is A cosinus theta. Right, because if you take A and multiply it by cosinus theta, which is this part, divided by this part, let's call it A on B, which is the projection divided by A, right? This is the definition of cosinus, right? You take the one near divided by the big one on the triangular, so you get this. So you get this is false, and you get this beautiful A on B, right? This is the projection. And this is why this A times cosinus theta give you this projection. But in the formula, you have another problem. You have this B, the norm of B. So you don't take only the projection, you are taking it time the norm of B. But you don't really need the norm of B. But this is the dot product. This is what you get from the dot product. So this is not exactly the projection. So what can you do to get exactly the projection of A onto B? We can divide this by B, right? By the norm of B. But when you do that, you just get a value, right? And you don't really, you want a vector. And the vector is not just a value, it's also a direction. So let's, after we get rid of the norm of B that we don't need, let's take a vector in the direction of B because you want the projection of A onto B. This gives you the size, but I want also the direction. So let's give it here a unit vector in the direction of B. But what is it if I just, what is this unit vector in the direction of B? Maybe he will give me to write this. Here it is, beautifully right, as you see. So what it is, it's B, the vector B divided by the norm of B, right? This is the definition for a unit direction vector. So let's put it here instead of this B. I don't see where is my pointer. Instead of this, let's write it here. So let's erase this. Here it is, erasing very nicely. And let's write it down. So how do I write it down? I don't know. Let's take this. So you take B and divide it by the norm of B. But when you look on all of it, what you got is, if we sum it all up, is norm of A, norm of, well, norm of A, cosinus theta, right? Right? No, all of it, I can just call it, it would be more understandable if I just say A dot product of B, right? This is all of it. But we said we need to divide by norm of B once to take this out, and another norm of b here and b here. So here it is here. So divided by norm of b twice, let's do it just to the power of 2 squared, because it's twice, times this b that right over here, and b. So this is exactly the formula for the projection of A onto B for a non-orthonormal vector space, for non-orthonormal base. But this is the formula. This is the formula. You can see it right over here. Now, if I look for a orthonormal base, what will happen is that the formula will look much easier to read. You can see that this is just a inner product of the one that you want. It's exactly the projection. So in orthonormal base, you don't even need to change the dot product. That's why orthonormal base is so nice. Dot product directly give you coordinates projections. What a beautiful result. So this was about the projection and the relation to the dot product. You saw how it behaves without a orthonormal base. We need to make corrections, divide by b squared, norm of b squared, by an orthonormal base where the base, every vector is the norm vector of every vector is orthogonal to another. It gives you exactly the dot product. Nice results, nice connection. Thank you all for watching, and that's it for now.